Learning objectives. In this chapter, the user would learn the following aspects of Introduction to Embedded System. Embedded System Overview, Design Process, Computer Essentials, Microprocessor and Microcontrollers, Processor Technology, Embedded System on Chip, Input-Output Devices. Introduction. An embedded system is any electronic device that incorporates a computer in its implementation. The user of an embedded device is often not even aware that a computer is present in the device. The computer is used primarily to provide flexibility and to simplify the system design. Unlike a PC, program code is usually stored in ROM and not in a hard disk drive. Typically, the end user does not develop new software for the embedded device. With advances in VLSI technology, embedded systems have become so inexpensive that they are found in most of today's electronic devices. Definition of embedded systems. An embedded system is one that has computer hardware with software embedded in it as one of its important components. An embedded system is not a microprocessor used in a traditional computing application, desktop, laptop, workstation. An embedded system is a microprocessor used as a component in another piece of technology: cell phone, digital camera, portable digital assistant, household appliances, automobile anti-lock brake system. Characteristics of embedded computing applications. Embedded computing is in many ways much more demanding than the sort of programs that you may have written for PCs or workstations. On the one hand, embedded computing systems have to provide sophisticated functionality, complex algorithms. The operations performed by the microprocessor may be very sophisticated. For example, the microprocessor that controls an automobile engine must perform complicated filtering functions to optimize the performance of the car while minimizing pollution and fuel utilization. User interface. Microprocessors are frequently used to control complex user interfaces that may include multiple menus and many options. The moving maps in Global Positioning System (GPS) navigation are good examples of sophisticated user interfaces. Deadlines involve real time. Many embedded computing systems have to perform in real time. If the data is not ready by a certain deadline, the system breaks. In some cases, failure to meet a deadline is unsafe and can even endanger lives. In other cases, missing a deadline does not create safety problems, but does create unhappy customers. Missed deadlines in printers can result in scrambled pages. Multi-rate. Many embedded computing systems have several real-time activities going on at the same time. They may simultaneously control some operations that run at slow rates and others that run at high rates. Multimedia applications are prime examples of multi-rate behavior. The audio and video portions of a multimedia stream run at very different rates, but they must remain closely synchronized. Manufacturing cost. The total cost of building the system is very important in many cases. Manufacturing cost is determined by many factors, including the type of microprocessor used, the amount of memory required, and the types of input-output devices. Power and energy. Power consumption directly affects the cost of the hardware, since a larger power supply may be necessary. Energy consumption affects battery life, which is important in many applications, as well as heat consumption, which can be important even in desktop applications. Challenges in embedded computing applications. The following external constraints are one important source of difficulty in embedded system design. How much hardware do we need? We have a great deal of control over the amount of computing power we apply to our problem. We cannot only select the type of microprocessor used, but also select the amount of memory, the peripheral devices, and much more. If there is too little hardware, the system fails to meet its deadlines. If there is too much hardware, it becomes too expensive. How do we meet deadlines? It is entirely possible that increasing the CPU clock rate may not make enough difference to execution time, since the program speed may be limited by the memory system. How do we minimize power consumption? In battery-powered applications, power consumption is extremely important. Even in non-battery applications, excessive power consumption can increase heat dissipation. How do we design for upgradability? The hardware platform may be used over several product generations or for several different versions of a product in the same generation with few or no changes. Does it really work? Reliability is always important when selling products. Customers rightly expect that products they buy will work. The sources that make the design so difficult are complex testing. Exercising an embedded system is generally more difficult than typing in some data. The timing of data is often important, meaning that we cannot separate the testing of an embedded computer from the machine in which it is embedded. Limited observability and controllability. Embedded computing systems usually do not come with keyboards and screens. This makes it more difficult to see what is going on and to affect the system's operation. We may be forced to watch the values of electrical signals on the microprocessor bus, for example, to know what is going on inside the system. Moreover, in real-time applications, we may not be able to easily stop the system to see what is going on inside. Restricted development environments. The development environments for embedded systems, the tools used to develop software and hardware, are often much more limited than those available for PCs and workstations. The embedded system design process. Overview of the embedded system design process is aimed at with two objectives. First, it will give us an introduction to the various steps in embedded system design before we delve into them in more detail. Second, it will allow us to consider the design methodology itself. The figure summarizes the major steps in the embedded system design process. In this top-down view, we start with the system requirements. In the next step comes specification. Top-down design. We will begin with the most abstract description of the system and conclude with concrete details. The alternative is a bottom-up view in which we start with components to build a system. Bottom-up design steps are shown in the figure as dashed line arrows. We need bottom-up design because we do not have perfect insight into how later stages of the design process will turn out. During the design process, we have to consider the major goals of the design, such as manufacturing cost, performance, both overall speed and deadlines, and power consumption. Requirements. Requirements may be functional or non-functional. We must capture the basic functions of the embedded system, but functional description is often not sufficient. Typical non-functional requirements include performance. The speed of the system is often a major consideration both for the usability of the system and for its ultimate cost. Performance may be a combination of soft performance metrics such as approximate time to perform a user-level function and hard deadlines by which a particular operation must be completed. Cost. The target cost or purchase price for the system is almost always a consideration. Cost typically has two major components. Manufacturing cost, which includes the cost of components and assembly. Non-recurring engineering costs, that is NRE costs, include the personnel and other costs of designing the system. Physical size and weight. The physical aspects of the final system can vary greatly depending upon the application. For example, an industrial control system for an assembly line may be designed to fit into a standard size rack with no strict limitations on weight. But a handheld device typically has tight requirements on both size and weight that can ripple through the entire system design. Power consumption. Power, of course, is important in battery-powered systems and is often important in other applications as well. Power can be specified in the requirement stage in terms of battery life. Requirements analysis of a GPS moving map. The moving map is a handheld device that displays for the user a map of the terrain around the user's current position. The map display changes as the user and the map device change position. The moving map obtains its position from the GPS, a satellite-based navigation system. Functionality. This system is designed for highway driving and similar uses, not nautical or aviation uses that require more specialized databases and functions. The system should show major roads and other landmarks available in standard topographic databases. User interface. The screen should have at least 400 to 600 pixel resolution. The device should be controlled by no more than 3 buttons. Performance. The map should scroll smoothly. Upon power up, a display should take no more than 1 second to appear, and the system should be able to verify its position and display the current map within 15 seconds. Cost. The selling cost, that is the street price of the unit, should be no more than $100. Physical size and weight. The device should fit comfortably in any person's hand. Power consumption. The device should run for at least 8 hours on 4 AA batteries. Specification. The specification is more precise. It serves as the contract between the customer and the architects. The specification should be understandable enough so that someone can verify that it meets system requirements and overall expectations of the customer. It should also be unambiguous. The specification must be carefully written so that it accurately reflects the customer's requirements and does so in a way that can be clearly followed during design. Architecture design. Many implementation details should be refined that system block diagram into 2 block diagrams, one for hardware and another for software. These 2 more refined block diagrams are shown in the figure. The hardware block diagram clearly shows that we have one central CPU surrounded by memory and input-output devices. In particular, we have chosen to use 2 memories, a frame buffer for the pixels to be displayed and a separate program or data memory for general use by the CPU. Designing of components. The component design effort builds those components in conformance to the architecture and specification. The components will, in general, include both hardware, FPGAs, boards and so on, and software modules. Some of the components will be ready-made. In the moving map, the GPS receiver is a good example of a specialized component that will nonetheless be a pre-designed standard component. We can also make use of standard software modules. One good example is the topographic database. Hardware components: power supply, processor, memory, timers, serial communication ports, input-output circuits, system application specific circuits. Software components. The application software is required to perform the series of tasks. An embedded system has software designed to keep in view of 3 constraints: availability of system memory, availability of processor speed, the need to limit power dissipation when running the system continuously in cycles of wait for events, run, stop, and wake up. Real-time operating system, RTOS. RTOS defines the way the system works, which supervises the application software. It sets the rules during the execution of the application program. A small-scale embedded system may not need an RTOS. System integration. The components built are put together and see how the system works. If we debug only a few modules at a time, we are more likely to uncover the simple bugs and are able to easily recognize them. Only by fixing the simple bugs early will we be able to uncover the more complex or obscure bugs. Computer essentials. Embedded processors can be broken into two broad categories: ordinary microprocessors (MU-P) and microcontrollers (MU-C), which have many more peripherals on chip, reducing cost and size. Contrasting to the personal computer and server markets, a fairly large number of basic CPU architectures are used. There are von Neumann as well as various degrees of Harvard architectures, RISC as well as non-RISC and VLIW. Word lengths vary from 4-bit to 64 bits and beyond, mainly in DSP processors, although the most typical remain 8 or 16-bit. Most architecture comes in a large number of different variants and shapes, many of which are also manufactured by several different companies. For example, ARM. CISC. Reasons for complex instruction set computers. CISC is an acronym for Complex Instruction Set Computer and are chips that are easy to program and which make efficient use of memory. Since the earliest machines were programmed in assembly language and memory was slow and expensive, the CISC philosophy made sense and was commonly implemented in such large computers as the PDP-11 and the DEC System 10 and 20 machines. Most common microprocessor designs, such as the Intel 80x86 and Motorola 68K series, followed the CISC philosophy. But recent changes in software and hardware technology have forced a re-examination of CISC, and many modern CISC processors are hybrids implementing many RISC principles. CISC was developed to make compiler development simpler. It shifts most of the burden of generating machine instructions to the processor. For example, instead of having to make a compiler write long machine instructions to calculate a square root, a CISC processor would have a built-in ability to do this. CISC attributes: a two-operand format where instructions have a source and a destination, register to register, register to memory, and memory to register commands. Multiple addressing modes for memory, including specialized modes for indexing through arrays. Variable length instructions, where the length often varies according to the addressing mode. Instructions which require multiple clock cycles to execute. Example, Pentium is considered a modern CISC processor. Most CISC hardware architectures have several characteristics in common. Complex instruction decoding logic, driven by the need for a single instruction to support multiple addressing modes. A small number of general-purpose registers. This is the direct result of having instructions which can operate directly on memory and the limited amount of chip space not dedicated to instruction, decoding, execution, and microcode storage. Several special purpose registers. Many CTSC designs set aside special registers for the stack pointer, interrupt handling, and so on. This can simplify the hardware design somewhat at the expense of making the instruction set more complex. A condition code register which is set as a side effect of most instructions. This register reflects whether the result of the last operation is less than, equal to, or greater than 0 and records if certain error conditions occur. CISC disadvantages. Designers soon realized that the CISC philosophy had its own problems, including earlier generations of a processor family generally were contained as a subset in every new version. So instruction set and chip hardware become more complex with each generation of computers. So that as many instructions as possible could be stored in memory with the least possible wasted space, individual instructions could be of almost any length. This means that different instructions will take different amounts of clock time to execute, slowing down the overall performance of the machine. Many specialized instructions aren't used frequently enough to justify their existence. Approximately 20% of the available instructions are used in a typical program. CISC instructions typically set the condition codes as a side effect of the instruction. Not only does setting the condition codes take time, but programmers have to remember to examine the condition code bits before a subsequent instruction changes them. RISC. RISC, Reduced Instruction Set Computer. Principle: sacrifice everything for speed. Reduce the number of instructions, that is, make CPU simpler. Get rid of complex instructions which may slow down the CPU. Use simple addressing modes, less time spent to compute the address of an operand. Limit the number of accesses to the memory. If a given operation cannot be executed in one clock period, then do not implement it in an instruction. Extensive use of pipeline architecture in order to reach CPI is equal to 1, that is, one instruction per clock period. History. The first RISC projects came from IBM, Stanford, and University of California at Berkeley in the late 1970s and early 80s. The IBM 801, Stanford MIPS, and Berkeley RISC 1 and 2 were all designed with a similar philosophy, which has become known as RISC. Certain design features have been characteristic of most RISC processors. One cycle execution time. RISC processors have a CPI, clock per instruction, of 1 cycle. This is due to the optimization of each instruction on the CPU and a technique called pipelining. Pipelining is a technique that allows for simultaneous execution of parts or stages of instructions to more efficiently process instructions. Large number of registers, the RISC design philosophy generally incorporates a large number of registers to prevent large amounts of interactions with memory. RISC attributes. The main characteristics of RISC microprocessors are extensive instructions, complex and efficient machine instructions, micro-encoding of the machine instructions, extensive addressing capabilities for memory operations, relatively few registers. RISC main features: limited number of instructions in the instruction set, 30 to 40 instructions versus 100 to 200 in the case of CISC. No complex instructions. Every instruction executes only one operation. Instructions have fixed format, fixed length, few combinations of fields inside the instruction code. Instructions executed in one clock period, except load and store instructions. Through intensive use of pipeline architecture, every instruction has the same number of pipeline stages. Only two instructions operate, that is, have access to the memory locations. Load, read data from the memory into a register. Store, write the data from a register into the memory. Load and store instructions require two accesses to the memory. One to read the instruction code, one to read or write the data. Load and store instructions are the only instructions which are executed in two clock periods. All the other instructions from the set are operating with registers or a register and a constant. Hard to write applications in assembly language, lack of more powerful instructions and addressing modes. Performance of RISC versus CISC. Hard to tell which is the best. A combination of CISC and RISC may be the solution. RISC inside, CISC outside. See Pentium processors. Complex instructions translated into simple RISC instructions. RISC pipelines. A RISC processor pipeline operates in much the same way, although the stages in the pipeline are different. While different processors have different number of steps, they are basically variations of these five used in MIPS R3000 processor. Fetch instructions from memory, read registers and decode the instruction, execute the instruction or calculate an address, access an operand in data memory, write the result into a register. Examples of RISC architecture. Academic implementations. RISC 1, 2. Berkeley University, Professor Patterson, 1980. MIPS, University of Stanford, Professor Hennessy, 1982. First commercial implementations. IBM 801 by the company IBM, 1975. Alpha by the company DEC. Spark, SPARC by Sun Microsystems, 1987. General purpose processors. PowerPC, IBM, Motorola. ARM architecture. Applications of RISC architectures. Powerful workstations used for engineering purposes, for example SunStation. High-end graphical stations used for simulation, animation, etc. Microcontrollers used for control applications and peripheral devices. Digital signal processors used for signal processing. Mobile devices, iPad, tablet, support for Android systems. RISC disadvantages. There is still considerable controversy among experts about the ultimate value of RISC architecture. Its proponents argue that RISC machines are both cheaper and faster and are therefore the machines of the future. However, by making the hardware simpler, RISC architectures put a greater burden on the software. Is this worth the trouble? Because conventional microprocessors are becoming increasingly fast and cheap anyway. Memory types. Many types of memory devices are available for use in modern computer systems. As an embedded software engineer, you must be aware of the differences between them, understand how to use each type effectively. Keep in mind that the development of these devices took several decades and that their underlying hardware differs significantly. The names of the memory types frequently reflect the historical nature of the development process and are often more confusing than insightful. The figure classifies the memory devices. Types of memory. Dynamic RAM, DRAM, DRAM. Static RAM, SRAM. Mask read-only memory, ROM. Programmable read-only memory, PROM. UV erasable programmable read-only memory, UVEPROM. EEPROM and Flash ROM. RAM. The RAM can be both read and written and is used to hold the programs, operating systems, and data required by computer system. In embedded systems, it holds the stack and temporary variables of the programs, operating system, and data. RAM characteristics. RAM is generally volatile. It does not retain the data stored in it when the system's power is turned off. Any data that needs to be stored while the system is off must be written to a permanent storage device such as a flash memory or hard disk. Example, a mobile phone has 128 KB or 256 KB of RAM to hold the stack and temporary variables of the program's operating system and data. Types of RAM. The RAM family includes two important memory devices, static RAM, SRAM, and dynamic RAM, DRAM. The primary difference between them is the lifetime of the data they store. SRAM retains its contents as long as electrical power is applied to the chip. If the power is turned off or lost temporarily, its contents will be lost forever. DRAM, on the other hand, has an extremely short data lifetime, typically about 4 milliseconds. This is true even when power is applied constantly. Compared to that, DRAM seems kind of useless. A simple piece of hardware called a DRAM controller can be used to make DRAM behave more like SRAM. The job of the DRAM controller is to periodically refresh the data stored in the DRAM. By refreshing the data before it expires, the contents of memory can be kept alive for as long as they are needed. So, DRAM is as useful as SRAM after all. When deciding which type of RAM to use, a system designer must consider access time and cost. SRAM devices offer extremely fast access times, approximately 4 times faster than DRAM, but are much more expensive to produce. Generally, SRAM is used only where access speed is extremely important. A lower cost per byte makes DRAM attractive whenever large amounts of RAM are required. Many embedded systems include both types, a small block of SRAM, a few kilobytes, along a critical data path, and a much larger block of DRAM for everything else. DRAM, SRAM static RAM and DRAM dynamic RAM used for saving the variables, stacks, process control blocks, input buffer, output buffer, decompress format of program, and data at the ROM image. Capacitor-based memory. Regular refresh is required, high power consuming, cheap, large access time, relatively small memory size demand, tens of megabytes. 1 or 2 chips would provide sufficient capacity. No need for expandability, 1 or 2 ranks. No need for sockets, short traces. Examples: graphic cards, network routers, Sony PlayStation. Lower latency, higher cost. Diverse requirements. Graphic cards favor streaming. Network equipment favors random access of 40-byte IP packets or 53-byte ATM packets. ROM. Contents of the read-only memory cannot be modified by the computer but may be read. A system has ROM units for bootstrap programs, basic input-output system, BIOS programs, and for vector addresses for the interrupts. Used to hold bootstrap program that is executed automatically by the system every time it is turned on or reset. Instruct the system to load its operating system off. Types of ROM. Masked read-only memory. Mask ROM is, from the software developer's perspective, read-only. A mask is provided by the company for which the chips are being produced. Such devices are therefore sometimes referred to as factory programmed. Programmable read-only memory, PROM. PROM is a form of write once, read many, that is WORM, or one-time programmable OTP memory. Basically, we use a PROM programmer to blow tiny fuses in the device. EPROM, erasable and programmable ROM. An EPROM is programmed in exactly the same manner as a PROM. However, EPROMs can be erased and reprogrammed repeatedly. To erase an EPROM, you simply expose the device to a strong source of ultraviolet light. ROM uses language-specific bits for the fonts corresponding to each character to a printer or display unit. Images bits for a display. Pictogram bytes for the full bit image corresponding to the pixels for a pictogram. Sequential changes at the inputs of display unit repeatedly generate the full pictogram. In a CISC as a control ROM at a microprogrammed unit for implementing instructions. Hybrid types. As memory technology has matured in recent years, the line between RAM and ROM has blurred. Now, several types of memory combine features of both. These devices do not belong to either group and can be collectively referred to as hybrid memory devices. Hybrid memories can be read and written as desired, like RAM, but maintain their contents without electric power, just like ROM. Two of the hybrid devices, EEPROM and Flash, are descendants of ROM devices. These are typically used to store code. The third hybrid, NVRAM, is a modified version of SRAM. NVRAM usually holds persistent data. EEPROM. EEPROMs are electrically erasable and programmable. Internally, they are similar to EPROMs, but the erase operation is accomplished electrically rather than by exposure to ultraviolet light. Any byte within an EEPROM may be erased and rewritten. Once written, the new data will remain in the device forever, or at least until it is electrically erased. The primary trade-off for this improved functionality is higher cost. Though write cycles are also significantly longer, than writes to a RAM. So you wouldn't want to use an EEPROM for your main system memory. EEPROM uses used during the program run to save non-volatile data and results. For example, date and time of a transaction, present port status, port driving history, system malfunctions history, etc. Electrically erasable by writing a byte or a set of bytes with all ones, and electrically programmable during a program run 1 byte right at each write instance. Flash memory. Flash memory combines the best features of the memory devices described thus far. Flash memory devices are high density, low cost, non-volatile, fast to read but not to write, and electrically reprogrammable. These advantages are overwhelming, and as a direct result, the use of flash memory has increased dramatically in embedded systems. From a software viewpoint, Flash and EEPROM technologies are very similar. The major difference is that flash devices can only be erased one sector at a time, not byte by byte. Typical sector sizes are in the range 256 bytes to 16 KB. Despite this disadvantage, Flash is much more popular than EEPROM and is rapidly displacing many of the ROM devices as well. Flash memory applications, ROM image and OS. Used during the program run to save non-volatile data and results. For example, a picture in a digital camera, voicemail. Storing SMS, MMS messages in a mobile phone, phone book, address book, etc. Storing voice compressed form in a voice recorder. Recall of pre-recorded message from a telephone exchange. Organizing memory. A memory, a data byte, or a word, or a double word, or a quad word may be accessed from or at all addressable locations with a similar process. It would be used to access from all locations, and there would be equal access time for a read or for a write that is independent of a memory address location. This mode differentiates from another model called serial access mode. Random access model of memory. Simple model for RAM and ROM. Both has random access model of memory. All memory operations take the same amount of time independent of the address of the byte or word at the memory. Addresses. Memory, both RAM and ROM, divided into a set of storage locations, each of which can hold 1 byte, that is 8 bits of data. The storage locations are numbered, and the number of a storage location, called its address, is used to tell the memory system which location the processor wants to reference. An important characteristic of a computer system is the width of the addresses it uses, which limits the amount of memory that the processor can address. Most current computers use either 32-bit or 64-bit addresses, allowing them to access either 232 or 264 bytes of memory. Example, assume that the memory system will support 2 operations: load, read operation into processor from memory, and store, read operation from processor into memory. Load from one set of addresses, 2 or 4, will take same time for store from another set of addresses, 2 or 4. Microprocessor. A microprocessor is a single chip semiconductor device, also which is a computer on chip, but not a complete computer. Its CPU contains an ALU, a program counter, a stack pointer, some working register, a clock timing circuit, and interrupt circuit on a single chip. To make complete microcomputer, one must add memory, usually ROM and RAM, memory decoder, an oscillator, and a number of serial and parallel ports. The CPU is a unit that centrally fetches and processes a set of general purpose instructions. The CPU instruction set includes instructions for data transfer operations, ALU operations, stack operations, input and output operations, and program control, sequencing, and supervising operations. The general purpose instruction set is always specific to a specific CPU. Any CPU must possess the following basic functional units: a control unit to fetch and control the sequential processing of a given command or instruction and for communicating with the rest of the system; an ALU for the arithmetic and logical operations on the bytes or words. It may be capable of processing 8, 16, 32 or 64-bit words at an instant. The earlier generation microprocessors' fetch and execute cycle was guided by clock frequency of the order of 1 MHz. Processors now operate at clock frequency of 2 GHz. Intel released a 2 GHz processor on August 25, 2001. This also marked the 20th anniversary of the introduction of the IBM PC. Intel released 3 GHz Pentium 4 on April 14, 2003. Since early 2002, a few highly sophisticated embedded systems, for example GBPS transceiver and encryption engine, have incorporated the gigahertz processor. GBPS means gigabit per second. Transceiver means a transmitting cum receiving circuit with appropriate processing and controls, for example for bus collisions. Example for microprocessor. One example of an older microprocessor is Intel 8085. It is an 8-bit processor. Another is Intel 8086 generation or 8088, which is a 16-bit processor. Intel 80x86, also referred to as x86 processors, are the 32-bit successors of 8086. The X here means extended 8086 for 32 bits. Examples of 32-bit processors is 80x86 series are Intel 80386 and 80486. Mostly, the IBM PCs use 80x86 series of processors, and the embedded systems incorporated inside the PC for specific tasks like graphic accelerator, disk controllers, network interface card use these microprocessors. Microcontroller. 8051 is an excellent device for building many embedded systems. One important factor is that 8051 requires a minimum number of external components in order to operate. It is a well-tested design. Introduced in its original form by Intel in the year 1980, the development costs of this device now start at less than $1. At this price, you get a performance of around 1 million instructions per second and 256 bytes, not megabytes, of on-chip RAM, 32 port pins and a serial interface. The main features of 8051 microcontroller are RAM, 128 bytes of data memory, ROM, 4 KB. Serial port using UART makes it simpler to interface for serial communication. 2 16-bit timer or counter, input-output pins, 4 ports of 8 bits, each on a single chip. 6 interrupt sources. 8-bit ALU, arithmetic logic unit. Harvard memory architecture. It has 16-bit address bus, each of RAM and ROM, and 8-bit data bus. 8051 can execute 1 million one-cycle instructions per second with a clock frequency of 12 MHz. Pin configuration of 8051. Pin 9. Pin 9 is the reset pin, which is used to reset the microcontroller's internal registers and ports upon starting up. Pin should be held high for 2 machine cycles. Pins 18 and 19. The 8051 has a built-in oscillator amplifier. Hence, we need to only connect a crystal at these pins to provide clock pulses to the circuit. Pins 40 and 20. Pins 40 and 20 are VCC and ground respectively. The 8051 chip needs plus 5 volt 500 mA to function properly. Although there are lower powered versions like the Atmel 2051, which is a scaled down version of 8051 which runs on plus 3 volts. Pins 29, 30 and 31. As described in the features of the 8051, this chip contains a built-in flash memory. In order to program this, we need to supply a voltage of plus 12 volt at pin 31. If external memory is connected, then pin 31, also called EA or VPP, should be connected to ground to indicate the presence of external memory. Pin 30 is called ALE, Address Latch Enabled, which is used when multiple memory chips are connected to the controller and only one of them needs to be selected. Pin 29 is called PSEN. This is Program Store Enabled. In order to use the external memory, it is required to provide the low voltage on both PSEN and EA pins. Ports. There are 4 8-bit ports: P0, P1, P2 and P3. Port P1, pins 1 to 8. The port P1 is a general purpose input-output port which can be used for a variety of interfacing tasks. The other ports P0, P2 and P3 have dual roles or additional functions associated with them based upon the context of their usage. Port P3, pins 10 to 17. Port P3 acts as a normal I/O port, but port P3 has additional functions such as serial transmit and receive pins, 2 external interrupt pins, 2 external counter inputs, read and write pins for memory access. Port P2, pins 21 to 28. Port P2 can also be used as a general purpose 8-bit port when no external memory is present. But if external memory access is required, then port P2 will act as an address bus in conjunction with port P0 to access external memory. Port P2 acts as A8 to A15. Port P0, pins 32 to 39. Port P0 can be used as a general purpose 8-bit port when no external memory is present, but if external memory access is required, then port P0 acts as multiplexed address and data bus that can be used to access external memory in conjunction with port P2. P0 acts as AD0 to AD7. The external interface of the standard 8051. Small 8051. Low-cost members of the 8051 family with reduced number of port pins and no support for off-chip memory. Typical application: low-cost consumer goods. Standard 8051. The small 8051s and the extended 8051s are derived. Extended 8051. Members of the 8051 family with extended range of no chip facilities, for example, CAN controllers, ADC, DAC, etc. Large number of port pins, and in recent devices, support for large amounts of off-chip memory. Typical applications: industrial and automotive systems. Reset requirements. Reset routine must be run to place hardware into an appropriate state before it can begin executing the user program. Running this reset routine takes time and requires that the microcontroller's oscillator is operating. Where system is supplied by a robust power supply, which rapidly reaches its specified output voltage when switched on, rapidly decreases to 0 volts when switched off, and while switched on cannot brown out, that is drop in voltage, then we can safely use low cost reset hardware based on a capacitor and a resistor to ensure that system will be reset correctly. This form of reset circuit is shown in the figure. Clock frequency and performance. All digital computer systems are driven by some form of oscillator circuit. The 8051 is certainly no exception. If the oscillator fails, the system will not function at all. If the oscillator runs irregularly, any timing calculations performed by the system will be inaccurate. The 8051 memory architecture. There are two distinct memory regions in an 8051 device: the data area and the code area. Data memory. Data memory is used to store variables and the program stack while the program is running. The data area will be implemented using some form of RAM. Most of the data area has a byte-oriented memory organization. However, within the data area is a 16-byte B data area which can also be accessed using bit addresses. The compiler avoids confusion if 0 into 24 in bit address and byte address. Code memory. Code area is used to store the program code, usually in some form of ROM. The code area may also contain read-only variables, constants, such as filter coefficient or data for speech playback. 8-bit family, 16-bit address space. An 8-bit microcontroller refers to the size of the registers and data bus. This means that the family will handle 8-bit data very quickly and process 16-bit or 32-bit data rather efficiently. The 16-bit address space means that the device can directly address 216 bytes of memory, that is 64 kilobytes. Input-output pins. Most 8051s have 4 8-bit ports, giving a total of 32 pins you can individually read from or control. All of the ports are bidirectional, that is, they may be used for both input and output. Timers. All members of the 8051 family have at least 2 timer or counters, known as timer 0 and timer 1. Most also have an additional timer, timer 2. These are 16-bit timers which can hold values from 0 to 65,535 in decimal. There are many things we can do with such a timer. It is used to measure intervals of time. It can measure the duration of a function by noting the value of a timer at the beginning and at the end of a function call and compare the two results. It can be used to generate precise hardware delays. It can be used to generate timeout facilities. This is a key requirement in systems with real-time constraints. Most important of all, it can be used to generate regular ticks and drive an operation system. Interrupts. An interrupt is a hardware mechanism used to notify a processor that an event has taken place. Such events may be internal events, such as the overflow of a timer, or external events, such as the arrival of a character through a serial interface. The original 8051-8052 architecture supported 7 interrupt sources. 2 or 3 timer or counter interrupts, 2 UART related, two external interrupts. The power on reset POR interrupt. In figure, the system executes two background functions, function 1 and function 2. During the execution of function 1, an interrupt is raised, and an interrupt service routine, ISR1, deals with this event. After the execution of ISR1 is complete, function 1 resumes its operation. During the execution of function 2, another interrupt is raised, this time dealt with by ISR2. Serial interface. Such an interface is common in embedded processors and is widely used. Here are some examples. The serial port may be used to debug embedded applications using a desktop PC. The serial port may be used to load code into flash memory for in-circuit programming. The serial port may be used to transfer data from embedded data acquisition systems to a PC or to other embedded processors. Power consumption. All modern implementations of 8051 processors have at least 3 operating modes: normal mode, idle mode, power down mode. The idle and power down modes are intended to be used to save power at times when no processing is required. We generally aim for an average power consumption of less than 10 mA. Idle mode. In the idle mode, the oscillator of the C501 continues to run, but the CPU is gated off from the clock signal. The interrupt system, the serial port, and all timers are connected to the clock. The idle mode is entered by setting the flag bit idle, pcon.0. The easiest way is pcon is equal to 0 into 01, 2/, enter idle mode. There are two ways, as activate in any enabled interrupt and perform a hardware reset. Power down mode. The power down mode is entered by setting the flag bit PDE pcon.1. This is done in C as follows: pcon is equal to 0 into 02, 2/, enter power down mode. The only exit from power down mode is a hardware reset. Microcontroller features. Benefits. Typically, low power or low cost. Target for embedded applications. Easily programmable. Simple ISAs, RISC processors. Use of development kits simplifies process. Limitations. Small storage space, registers and memory. Restricted instruction set. May be required to multiplex pins. Not typically used for high performance. PIC microcontroller. PIC 16F684. High performance, low cost for embedded applications. Only 35 different instructions. Interrupt capability. Direct, indirect, relative addressing mode. Low power. 8.5 UA, 32 kHz, 2 volts. Peripheral features. 12 input-output pins with individual direction control, 10-bit AD converter, 8 or 16-bit timer or counter. Special microcontroller features. Internal or external oscillator, power saving sleep mode. High endurance flash or EEPROM cell, 12 pins, 2048 instructions, 128 byte variable memory, ADC, comparator, timers, ICD. Peripheral Interface Controller PIC was originally designed by General Instruments. PIC was sold to Microchip. CPU. A PIC CPU consists of several subunits such as instruction decoder, ALU, accumulator, control unit, etc. It normally supports Reduced Instruction Set Computer RISC architecture. RISC design, in which most of the instructions a computer decodes and executes, are simple. Memory. The memory in a chip used to store the data and programs temporarily or permanently. As like normal microcontrollers, the PIC chip also has certain amount of RAM, ROM, EPROM, other flash memory, etc. ALU. Perform operations on temporary working register and register file. 8-bit wide ALU. One of the operand is normally in W register and the other is either a fin register or an immediate constant. Affect various flags, namely carry, digit carry, 0 in status register. PAR on reset. The task of POR is ensuring that the processor starts at known address when PAR is first on. The reset function will set the program counter to the starting. PAR up timer. A special timer that delays that start of program execution after the PIC has been reset on PAR. This time delay allows VDD to rise to the required level. Brown out delay. When the power supply drops below a certain voltage, 4 volts in case of PIC, it causes PIC to reset. Program memory space. 13-bit program counter to address 8K locations. Each location is 14-bit wide. Instructions are 14 bits long. Reset vector is 0000H. When the CPU is reset, its PC is automatically cleared to 0. Interrupt vector is 0004H. 0004H is automatically loaded into the program counter when an interrupt occurs. Vector, address of code to be executed for given interrupt. Process. A processor is the heart of the embedded system. For an embedded system designer, knowledge of microprocessor and microcontroller is a must. Processor technology. A processor is a digital circuit designed to perform computation tasks. The architecture of the computation engine used to implement a system's desired functionality. Processor does not have to be programmable. Processor not equal to general purpose processor. General purpose processor. Programmable device used in a variety of applications, also known as microprocessor. Features. Program memory. General data path with large register file and general ALU. User benefits. Low time to market and NRE costs. High flexibility. Pentium, the most well known, but there are hundreds of others. The general processor types, their characteristics and examples. Interesting links for choosing the right processor type for your application. Here are some general characteristics from a general purpose processor. Advantages. Easy to design and use. Design time is thus low. Design cost is low. Reprogrammability. Disadvantages. Performance is not very good. Size is high because they are built to be used in a variety of applications with different specifications, and all these specifications must be possible on the processor. They consume much power. Usually, they are used to put in a product the first time it goes to the market because of their cheap design cost and ease to use. Because of the use of code, a designer usually strives to minimize compiled code size rather than maximize performance. Single-purpose processors. Digital circuit designed to execute exactly one program, aka coprocessor, accelerator, or peripheral. Features. Contains only the components needed to execute a single program. No program memory. Benefits. Fast, low power, small size. This type of processor is designed to execute exactly one program. An embedded designer creates a single-purpose processor by designing a custom digital circuit. Advantages and disadvantages are more or less the opposite of the general purpose processor. Advantages: performance is very good, small size, exact to fit one solution, they consume little power. Disadvantages: not very easy to design and design time is high, design cost is thus higher, reprogramming is difficult. Limited flexibility, not easy to make changes or accommodate features. The standard single purpose processors, hardware peripherals, are explained in a different chapter. They are used for in a wide variety of applications for the same task. Single purpose processors. Example: they are designed to fit the specific requirements of an end product. In the design process, they will be optimized for both power and performance. An ASIC is introduced for a product usually after a product is stabilized on the market with non-ASIC solution because of the higher development time and cost. After stabilization, the producer can look for extra margin by making the processor as good as possible for his application. A disadvantage is that when you make a mistake, you will need to make a whole new chip. But for a general purpose processor, you just change the code and recompile. You can use an ASIC in a stable market where technology and requirements aren't going to change rapidly. Application-specific processors. Programmable processor optimized for a particular class of applications having common characteristics. Compromise between general purpose and single purpose processors. Features: program memory, optimized data path, special functional units. Benefits: some flexibility, good performance, size and power. An ASIP is designed for a particular class of applications with common characteristics. It's an intermediate solution between a general purpose and a single purpose processor and gives more flexibility than a single purpose processor and still better performance, power, size than a general purpose processor. Of course, this leads to a longer design time, which means costs, and there is also a compiler problem. You will have to create your compiler usually yourself. Example: Digital Signal Processor, DSP. A DSP is optimized to efficiently perform repetitive and numerically intensive tasks such as matrix operations, convolution for filtering in real time because of the performance limitations of the MCUs. DSPs can run at very high clock rates and they are often compared in terms of how many millions of MAC operations they can perform per second. This metric is known as mega MACs or MMACs. A DSP is optimized to do mathematical operations but not for supervisory control. Thus, DSP-based systems are integrated with the slower MCUs. This can be done in two ways. Advantage: design of DSP and MCU separate from each other. Disadvantages: hand partitioning between control and DSP function. If there are too many instructions for the DSP, the MCU can't take over. The DSP and MCU require different development tools. Convergent processor for computation on real-time data flows and for control-oriented tasks. Advantages: optimized for computation on real-time data flows as well as for control-oriented tasks. High clock rates and lower power dissipation. Disadvantages: mixing a control application with signal processing on the same device. Non-real-time tasks may interfere with time-critical tasks. The skills of developers must be higher. Embedded System on Chip, SoC. Introduction. SoC is a system on a VLSI chip that has all needed analog as well as digital circuits, processors, and software, for example, single chip mobile phone. A system could be a computer, PDA, mobile phone, MP3, digital camera, or customized for specific purposes. The system may contain digital, analog, mixed signal, and often radio frequency functions. SoC refers to integrating all components into a single integrated circuit chip. A system on a chip or system on chip, SoC or SoC, is an integrated circuit that integrates all components of a computer or other electronic system into a single chip. It may contain digital, analog, mixed signal, and often radio frequency functions, all on a single chip substrate. SoCs are very common in the mobile electronics market because of their low power consumption. A typical application is in the area of embedded systems. The contrast with a microcontroller is one of degree. Microcontrollers typically have under 100 KB of RAM, often just a few kilobytes, and often really are single chip systems, whereas the term SoC is typically used for more powerful processors capable of running software such as the desktop versions of Windows and Linux, which need external memory chips, flash RAM, to be useful, and which are used with various external peripherals. Structure of a system: microcontroller, microprocessor, or DSP cores. Memory blocks: ROM, RAM, EEPROM, flash. Clock sources: local oscillator, PLL. Power circuits: voltage regulator, DC-DC, converters, etc. Peripherals: counter timers, real-time timers, etc. External interfaces: USB, Ethernet, UART, RS-232, etc. Analog interfaces: ADCs and DACs. Blocks are connected by either a proprietary or industry standard bus. Embedded software. Design flow. A SoC consists of both the hardware described above and the software controlling the microcontroller, microprocessor, or DSP cores, peripherals, and interfaces. The design flow for a SoC aims to develop this hardware and software in parallel. Most SoCs are developed from pre-qualified hardware blocks for the hardware elements described above, together with the software drivers that control their operation. Of particular importance are the protocol stacks that drive industry standard interfaces like USB. The hardware blocks are put together using CAD tools. The software modules are integrated using a software development environment. Fabrication. SoCs can be fabricated by several technologies, including full custom design, which is a methodology for designing integrated circuits by specifying the layout of each individual transistor and the interconnections between them. Standard cell methodology, which is an example of design abstraction whereby a low-level VLSI layout is encapsulated into an abstract logic representation such as a NAND gate. Cell-based methodology, the general class to which standard cells belong, makes it possible for one designer to focus on high-level logical function aspect of digital design, while another designer focuses on the implementation or physical aspect. A field programmable gate array, FPGA, is an integrated circuit designed to be configured by a customer or designer after manufacturing. The FPGA configuration is generally specified using a hardware description language, HDL, similar to that used for an application-specific integrated circuit, ASIC. Timers and counters. Introduction to counters or timers. Counter timer hardware is a crucial component of most embedded systems. In some cases, a timer is needed to measure elapsed time. In others, we want to count or time some external events. Here's a primer on the hardware. Counter timer hardware is a crucial component of most embedded systems. In some cases, a timer measures elapsed time. counting processor clock ticks. In others, we want to count or time external events. The names counter and timer can be used interchangeably when talking about the hardware. The difference in terminology has more to do with how the hardware is used in a given application. Timers and counters. The figure shows a simple timer similar to those often included on chip within a microcontroller. You could build something similar from a couple of 74HC161 counters or a programmable logic device. The timer shown consists of a loadable 8-bit count register, an input clock signal, and an output signal. Timers and counters, semi-automatic. A timer with automatic reload capacity will have a latch register to hold the count written by the processor. When the processor writes to the latch, the counter register is written as well. When the timer later overflows, it first generates an output signal. Then, it automatically reloads the contents of the latch into the count register. Since the latch still holds the value written by the processor, the counter will begin counting again from the same initial value. Such a timer will produce a regular output with the same accuracy as the input clock. This output could be used to generate a periodic interrupt like a real-time operating system RTOS timer tick, provide a baud rate clock to a UART, or drive any device that requires a regular pulse. Timers and counters. Input capture. An input capture timer, like the one shown in the figure, has a latch connected to the timer's count register. The timer is run at a constant clock rate, usually a derivative of the processor clock, so that the count registers is constantly incrementing or decrementing for a down counter. An external signal latches the value of the free running timer into the processor visible register and generates an output signal, typically an interrupt. Options abound. Many timers provide a means to pre-sale the input clock signal. For example, the 8-bit timer in Atmel's AT90S8515 microcontroller can be incremented with every processor clock cycle. Every 4th, every 64th, every 256th, or every 1024th. Selecting a less frequent update cycle is called pre-scaling the input clock. Similarly, each increment could occur on either the rising or falling edge of some other signal entirely. In the Atmel part, these features are software selectable. Watchdog timers. It is timing device such that it is set for a preset time interval and an event must occur during that interval, and program instruction must disable the watchdog timer. Otherwise, the device will generate an timeout signal and interrupt for the failure to get that event in watch time interval. On that event, the watchdog timer is disabled to disable generation of timeout or reset. Timeout may result in processor start a service routine or start from beginning. A watchdog timer is a piece of hardware that can be used to automatically detect software anomalies and reset the processor if any occur. Generally speaking, a watchdog timer is based on a counter that counts down from some initial value to 0. The embedded software selects the counter's initial value and periodically restarts it. If the counter ever reaches 0 before the software restarts it, the software is presumed to be malfunctioning and the processor's reset signal is asserted. The processor and the embedded software it's running will be restarted as if a human operator had cycled the power. Watchdog timers example. Assume that we anticipate that a set of tasks must finish in 100 milliseconds interval. The watchdog timer is disabled and stopped by the program instruction in case the tasks finish within 100 milliseconds interval. In case task does not finish, not disabled by the program instruction, the watchdog timer generates interrupts after 100 milliseconds and executes a routine which is programmed to run because there is failure of finishing the task in anticipated interval. Watchdog timer application. An application in mobile phone is that display is off in case no GUI interaction takes place within a watch time interval. The interval is usually set at 15 seconds, 20 seconds, 25 seconds or 30 seconds in mobile phone. This saves power. An application in temperature controller is that if controller takes no action to switch off the current within preset watch time interval, the current is switched off and warning signal is raised as indication of controller failure. Failure to switch off current may burst a boiler in which water is heated. Interrupt controller. The interrupt controller manages the interrupts from up to 256 sources with up to 16 priority levels for an embedded system. The interrupt controller is fully configurable at design time. Each interrupt source can be assigned a priority under program control and interrupts can be dynamically masked or enabled. A global priority level register enables masking of lower priority levels. The priority of the last interruption can be read by software. The interrupt controller has the following features: up to 256 interrupts, up to 16 priority levels, dynamically assignable priority levels, standard APS bus interface. Typically, a computer system, including embedded systems, has an interrupt controller. x86 based computer system, general purpose computer system, has 3 interrupt controllers: local A PIC, advanced PIC. Input-output APIC 8259. Interrupt controller receives interrupt requests from input-output devices and sends an interrupt signal to CPU. x86 allocates 2 input pins for interrupt: INTR, NMI. ARM provides 2 input pins as well: NIRQ, NFIQ. Interrupt controller provides registers with which programmers can assign priority to each interrupt source, mask specific interrupt inputs. Direct Memory Access (DMA). Direct Memory Access allows devices to transfer data without subjecting the processor a heavy overhead. Otherwise, the processor would have to copy each piece of data from the source to the destination. This is typically slower than copying normal blocks of memory, since access to input-output devices over a peripheral bus is generally slower than normal system RAM. During this time, the processor would be unavailable for any other tasks involving processor bus access, but it can continue to work on any work which does not require bus access. DMA transfers are essential for high-performance embedded systems where large chunks of data need to be transferred from the input-output devices to or from the primary memory. Input-output peripherals that acquire data that must be read signal the DMA controller to perform a DMA transfer by asserting a hardware DMA request signal (DRQ). A DMA request signal for each channel is routed to the DMA controller. When the DMA controller sees a DMA request, it responds by performing one or many data transfers from that input-output device into system memory or vice versa. Channels must be enabled by the processor for the DMA controller to respond to DMA requests. In bus master mode, the DMA controller acquires the system bus from the CPU to perform the 3 DMA transfers. The internal registers consist of source and destination address registers and transfer count registers for each DMA channel, as well as control and status registers for initiating, monitoring, and sustaining the operation of the DMA controller. DMA transfer types and modes. Single transfer. Each trigger causes a single transfer. The module will disable itself when number of transfers has occurred. The register allows these addresses to be incremented or decremented by 1 or 2 bytes with each transfer. This transfer halts the CPU. Block transfer. An entire block is transferred on each trigger. The module disables itself when this block transfer is complete. This transfer halts the CPU and will transfer each memory location one at a time. This mode disables the module when the transfer is complete. Burst block transfer. This is very similar to block transfer mode, except that the CPU and the DMA transfer can interleave their operation. This reduces the CPU to 20% while the DMA is going on, but the CPU will not be stopped altogether. The interrupt occurs when the block has completely transferred. This mode disables the module when the transfer is complete. Analog to digital conversion. Terminology. Analog. Continuously valued signal such as temperature or speed with infinite possible values in between. Digital. Discretely valued signal such as integers encoded in binary. Analog to digital converter. ADC or AD, A to D, converts an analog signal to a digital signal. Digital to analog converter. DAC, DA, D2A. An embedded system surroundings typically involve many analog signals. Analog to digital conversion. The ADC in the system microcontroller can be used in many applications such as data acquisition system, DAS, analog control system, and voice digitizing system. Suppose a system needs to read an analog input from a sensor or transducer circuit. If converted to bits by the ADC unit in the system, then these bits, after processing, can also give an output. This provides a control for automation by a combined use of ADC and DAC features. The converted bits can be given to the port meant for digital display. The bits may be transferred to a memory address, a serial port, or a parallel port. A processor may process the converted bits and generate a pulse code modulated output, PCM. Digital to analog converters. Digital to analog conversion is a lot like analog to digital conversion. A digital to analog converter, DAC or D to A, is a device for converting a digital, usually binary code to an analog signal, current, voltage, or electric charge. Digital to analog converters are interfaces between the abstract digital world and analog real life. Usually, DACs are used to convert 8-bit digital data into analog signal. If a greater precision is needed, chips with 12-bit, 14-bit, or 16-bit data convertibility are available. Almost all the DACs enable the user of the chip to define the high and low references of the analog output, provided that these references fall within a fixed range defined for that chip. Infrared devices. Infrared is a serial, half-duplex, line-of-sight based wireless technology for data communication between devices. Electronic wave frequencies just below visible light spectrum. Diode emits infrared light to generate signal. Infrared transistor detects signal, conducts when exposed to infrared light. Cheap to build. Need line of sight, limited range. Infrared protocol suite supports data transfer rates of up to 4 Mbps. Supports bidirectional serial communication over viewing angle between plus or minus 15 degrees and distance of nearly 1 meter. At 5 meters, the IR transfer data can be up to data transfer rates of 75 kbps. There should be no obstructions or wall in between the source and the receiver. Windows and the several operating system support. Infrared monitor in Windows monitors the IR port of the IR device. Detects a nearby IR source. Controls, detects, and selects the IR communication activity. On command, the device sets up connection using IRDA. On command, starts the IR communication. When IR communication is inactive, the monitor enables plug and play unless disabled. UART, Universal Asynchronous Receiver or Transmitter Device. Device connected to the system bus. It takes parallel data, converts it into RS-232C serial format and transmits it, and receives data in serial format and converts it to parallel format for CPU bus. Parallel byte is converted into start bit, 8 bits, parity bit, and stop bit serial form, and vice versa. Asynchronous transmission allows data to be transmitted without the sender having to send a clock signal to the receiver. Instead, the sender and receiver must agree on timing parameters in advance, and special bits are added to each word, which are used to synchronize the sending and receiving units. UART, the receiver, synchronizes with transmitter using the falling edge of the start bit. Samples the input data line at a clock rate that is normally a multiple of baud rate, typically 16 times the baud rate. Reads each bit in middle of bit period. Many modern UARTs use a majority decision of the several samples to determine the bit value. Removes the start and stop bits, optional calculates, and checks the parity bit. Presents the received data value in parallel form. UART transmitter. Transmitter converts data from parallel to serial format, inserts start and stop bits, calculates and inserts parity bit if required. Output bit rate is determined by the UART clock. Conclusion. In this chapter, the user have covered the following aspects of introduction to embedded system. Embedded system overview, design process, computer essentials, microprocessor and microcontrollers, processor technology, embedded system on chip, input-output devices.